Chapter 4 is entitled Discrete Random Variables, and basically what we're going to be doing is we're going to be discussing probability situations that involve discrete data. So remember that discrete data, as opposed to continuous, is data that typically can be counted. Okay, so there are certain values that are valid and other values that are not valid. So for example, if I asked you how many siblings you have, 3.2 would not be a valid answer. Okay, so if there are some answers that are not valid, then you're typically dealing with discrete data. So the first thing we're going to do in Chapter 4 is we're going to introduce the idea of a probability distribution function. This is often abbreviated PDF. So probability distribution functions for discrete variables typically look like tables. Okay. In the first column of the table, you'll have your random variables, and in the second column of the table, you'll have the probabilities. So a couple of important features of PDF tables is that every probability in the table needs to be between 0 and 1. Okay, we've discussed this in Chapter 3, that we basically say that a probability of 0 is something that never happens, and a probability of 1 is something that always happens. So you can't have a probability higher than 1, and you can't have a probability lower than 0. Finally, the second thing is that if you add all the probabilities up in that second column, the sum of all the probabilities should equal 1. Okay, because something is going to happen. One of those random variables is going to occur, and so the sum of all of the possible outcomes should always equal 1. Alright, so our first example here is we have a child psychologist interested in the number of times a newborn baby wakes his or her mother up in the middle of the night. And so basically we took 50 mothers and we obtained the following data. Okay, for each of these mothers, the number of times the baby woke them up was either 0, 1, 2, 3, 4, or 5. Okay, and I'm not giving you all of the probabilities separately. Instead, I'm going to go ahead and just give you the PDF, the probability distribution function, in this table form. Okay, which is typically the way they show up for discrete variables. So in the first column, notice that we have those 6 options for the number of times these mothers could have been woken up, from 0 through 5. And then in the right-hand column, we have the probability. So basically, out of these 50 mothers, 2 of them were woken up 0 times, 11 were awakened once, 23 twice, etc. Okay? And so what we do is we create a probability out of that. 2 out of 50, 2 50ths is the probability that one of these mothers would be woken up 0 times. 23 50ths is the probability that they'd be woken up twice. Okay? So a couple of things that we would want to do is just make sure that all the random variables are accounted for in the left-hand column, which they are. We want to make sure that each of the probabilities on the right side is between 0 and 1, which they all are. And then finally, and you can maybe pause the video and do this on your own just to double check, but we'd want to make sure that all of the probabilities on the right-hand column add up to 1. So in this case, we should see 50 out of 50, 50 50ths. For a second example, we're gonna do more of the same, but on this one, I would encourage you to pause the video after we discuss A and see if you can construct a PDF table, and then take a look and see when I show you the one that I have. So the idea is that we have a lady, Nancy, who has class, or a student named Nancy who has, I guess she could be a lady and a student, sorry about that. Anyway, she has class 3 days a week. Okay, she doesn't always go to class 3 days a week. 80% of the time she does, she goes 3 days. 15% of the time she goes 2 days a week. And 4% of the time she goes 1 day a week. And only 1% of the time does she not go at all. So what are the values that our random variable could take on? Well, basically it's the number of days that she could possibly attend class. So 3, 2, 1, and 0. Typically for PDFs, we'd want to, when we make the table, we'd want to put them in ascending order, so 0, 1, 2, 3, 4, 5. but that's not necessarily required. It's just kind of standard. All right, so with that information, you want to construct a PDF table. So if you want to pause the video for a moment and see if you can come up with a PDF table, and then when you're done, resume the video, and I'll show you the one that I have. Okay, so here is the PDF that I have, real simple. For 0, we have 0.01, which correlates to 1%, 1 at 0.04 or 4%, 2, 0.15, and 3 is 0.8. So this is basically it for section 1. This is what you need to be able to do is read a PDF table, be able to create a PDF table, and understand that what the table tells you is all the different possible values for the random variable and the associated probabilities for each of those values. Let me know if you have any questions. The practice examples here for the suggested homework should give you a pretty thorough cross-section of the kind of things that you're going to need. In section 4.2, we're going to talk about the mean and standard deviation of discrete PDFs. Note that the mean is also known as the expected value. If you repeat a trial, a procedure, many times, then the value that you would expect to get or expect to be very close to is the expected value, also known as the mean. Okay, so for example, just real simple, if you flip a coin 10 times, the expected number of heads would be 5. Okay, we know that with only 10 flips, it may not even be very close to 5. But if you do 1,000 flips, you should be pretty close to 500. And if you do 1,000,000 flips, you should be pretty close to 500,000 heads. So the more you do, according to the law of large numbers, the closer your observed probability is to your theoretical probability. So to find a mean, to find this expected value for a PDF, a discrete PDF, we multiply the values of the random variable by their associated probabilities, and then we add all of those results up. So for example, we have a men's soccer team, plays soccer either 0, 1, or 2 days a week. The probability they play 0 days is 0.2, probability of 1 day is 0.5, and the probability of 2 days is 0.3. So we want to find the long-term average or expected value, mu, of the number of days per week the men's soccer team plays soccer. So we're going to switch over to the document camera. This is a relatively simple example, but I think the document camera will be helpful just to kind of see the process. All right, so we're going to find the mean of this probability distribution function. And this process is real simple for finding the mean. We're going to multiply our x value times our probability. And we're going to do that for each row. So multiplying 0 times 0.2 gives me 0. 1 times 0.5 gives me 0.5. 2 times 0.3 gives me 0.6. And then I just add these results up. So 0.5 and 0.6 gives me 1.1. So the mean, okay, which we use mu for mean, that's just a lowercase Greek letter, will be 1.1. Okay, now this is also known as our expected value. So sometimes, our book doesn't use it, I don't think, but occasionally you might see it abbreviated EV for expected value. But just know that for our textbook, we're going to use mu. For example, 4.5, we're going to do something similar, except we have a few little differences. One is we only have 2 possibilities. Okay, here we either win or we lose. This is a game of chance where you're selecting 5 numbers from 0 to 9, and then you're going to, if you match the 5 numbers in order, then you win. So it costs $2 to play. You get $100,000 profit if you win, so you get your $2 back plus you get $100,000. And we want to find the long-term expected profit if you play this game over and over and over again. So once again, we'll go back to the document camera for this, and we'll see how this, what the little details are that you need to pay attention for this example. For example 4.5, we have a little different scenario going on, and so I didn't fill the probabilities out on this table like I did with example 4.3. Because I don't think it's quite as obvious. It's not necessarily given to you verbatim. So what we have to do is figure out, based on this game, what's the probability that we win and what's the probability that we lose. So this game had us pick 5 numbers, and that was with replacement. I don't know if you caught that, but it was with replacement. So, for example, like 33333 would be a legitimate choice. Okay, you can have the same number repeating. So to figure out the probability of winning, what we really need to do is figure out the total number of combinations. So for the first number, we have 10 things to choose from, right? 0 through 9. For the next number, because things can repeat, we have 10 again. For the third number, we have 10. For the fourth number, we have 10. And for the fifth number, we have 10. So if you multiply all of those up, we get, I'm just going to say 10 to the fifth. Okay. So yes, I could multiply that out and get, 1 with 5 zeros after it, but for now I'm just going to leave it as 10 to the fifth. So the probability of guessing the one correct number is 1 over 10 to the fifth, or if I wanted, I could say 10 to the negative fifth, right? In essence, this is what? 0.00001. Okay. For losing, though, this is the probability of winning. The probability of losing would be 1 minus that. So if we take 0.00001 and we subtract 1 minus that, we get 0.99959, right? So now we have our PDF completed. We have our table filled out. So now to find the mean, we need to multiply. So we'll do -2. I'm not going to try to write it up there because it's getting a little crowded. -2 times 0.99999 plus, and then what we win is $100,000, but the probability of that is much lower. Okay, 0.00001. So we need to get our calculator out, and I seem to be missing mine, and we need to calculate this. But if memory serves correctly, we get pretty close to -1 as our mean. Okay, forgive me for not being more prepared. I'm still unpacking from vacation. I'm not sure where my calculator is. So mu is approximately -1. And again, it's not exactly 1, but it's pretty close when you do the math. So what this tells you is, for a gambling type scenario like this, your expected value is actually a loss. Okay, if you were to play this game hundreds and hundreds of times, you might win once, but more likely not. So the average of your winnings, quote unquote, will actually be a loss of $1. Okay, this is how things like the lottery stay in existence, because yes, one person does occasionally win the lottery every few weeks, but overall, the people that are spending money on lottery tickets have an expected value of -1, or negative whatever it may be for that particular game. So the vast majority of people are putting money in. Rarely does someone pull money out, and so overall, the state or the casino or whatever ends up winning money. So hope that helps on the PDF and how we might face some slightly different scenarios occasionally where we have negative values. All right, standard deviation is something we've already discussed. Remember, we say it's how spread out the data is. So PDF tables have standard deviations as well. So calculating the standard deviation is a little more complicated than the mean, but it's still not too bad. It requires a couple extra steps. Okay, in this one, what we're going to do is we have to find the mean first. Okay, so if you don't already have the mean, you need that first. But then what you do is you subtract each of the values of the random variable from the mean. Okay, we take that difference and we square it, and then we multiply that square by the probability of that variable, that value of the variable. And then once we've done that, we add all of those products together and then finally take the square root. So we're going to do that soccer team example again where they played either 0, 1, or 2 days a week. We're going to look at that again on the document camera real quick to show you how to calculate standard deviation. Okay, for standard deviation, we're going back to the soccer team data or soccer team distribution. And so this was the original PDF for that. And we already figured out that the mean of this situation was 1.1. So I found my calculator. We're going to do the standard deviation calculations here, and I'm going to use my calculator to help me just because I don't want to make mistakes and have to correct them later. So we already know mu, so the first thing that we're going to do is we're going to add a little column here that's going to be x minus mu. So x in this case is 0, 0 minus 1.1 is negative 1.1, and then for the next one we have 1 minus 1.1, that would be negative 0.1, and then we have 2 minus 1.1, that would be positive 0.9. Alright, then the next thing we're going to do is we're going to take each of those things that we just found and we're going to square them. So this is where the calculator might come in handy. Negative 1.1 squared is positive 1.21. 0.1 squared is 0.01. Don't know why I did my calculator for that. I didn't need to. 0.9 squared is going to be 0.81. So now we take each of these and we add them up. So I'm just going to do a little plus there. So this is going to be 3 and 0 and 2, right? 2.03. Double check that. Oops. 2.03. Okay, good. So now this, just as a side note, this is what's called the variance. And the variance is its symbol is sigma squared. Oh, you can't see that. There we go. Variance is sigma squared. What we're looking for is the standard deviation, which is just sigma. Okay. Well, if we take the square root of 2.03, that will give us sigma, right? Because sigma squared is 2.03. Kind of makes sense. So let's see, there's the answer, and we get 1.42478. So I'm going to round that to 1.4, because typically we round these things to one more decimal place than is in the original data. So we have a standard deviation of 1.4 for these soccer players. All right, so that's it for section 2. In this homework, you're going to calculate some means, calculate some standard deviations, and hopefully get real familiar with how this works. And hopefully by the end, you'll be pros. But if you have any questions, please let me know. Reach out in classroom or via email, and I'll be happy, or in the office hours coming up, and I'll be happy to help you. Thanks.